Okay, so you will learn something about a program that I have jointly with Alessio Corti, and it's a program that goes for many years. We've been in Wolf 3 times, and it's one article out, and it has some relations to other people in the audience. So it's at the core, it's about constructing Fano manifolds, smoothing and resolving Fano varieties with single log structures. So it relates to some talks. We've had talks about logarithmic deformation theory from Simon, and we have had a talk when I wasn't here yet by Philip about zero-mutable all polynomials, and both of those things are related to what I'm speaking about. And I want to speak about a particular example. Is there any good one here? That's not working. Oh, this one's maybe okay. That might be okay. I'll complain when it runs out. So let's look at toric threefold singularities. So I'm going to do a little bit of repetition. I think what was also in Mate's talk. Get back to that. So that starts, I'm looking only at singularities that have a property of being Gorenstein. And then that means that I'm looking at a cone over a lattice polygon. Let's for the purpose of this talk of demonstration, let's look at this lattice polygon, which has a length 3 edge here and a length 2, and there's an interior point and an outside point here. This is a lattice polygon. You can take any other lattice polygon. Oh, thank you. And let me call this F, because later on it shows up as a face of some other one. I'll call it F for that reason. So lattice polygon, and then how do you get a toric variety or singular toric variety from this polygon? You take the cone of the polygon. That means you place the polygon in one extra dimension at height 1. So you add a new dimensions. You work in R2 times R now. And the new direction is this one. And then at that height 1, there's the polygon. And height 0, there's somewhere a point where you use as the origin of the cone. And then you just take the cone generated by that polygon. And that's now a rational polyhedral cone. Let's call this cone sigma. It has unusual toric geometry. And then the toric variety construct from dualizing that cone. So you go to the dual vector space. And in that dual vector space, you look at all the vectors that pair with this cone non-negatively, with all the points in the cone. That gets you a dual cone. And then you intersect that dual cone with a dual lattice. The lattice is because of three-dimensional space, you take the standard lattice in it, it's a dual space. And that intersection is a monoid. It's some people call it a semigroup. And then you take the monoid ring. That's just say coefficients in complex numbers. Now we have an ordinary C algebra. And then take the spectrum of that. And that's what Fulton calls the toric variety associated to this. Let's call it X sigma. So it depends on the cone, and of course that cone depends on the polytope. And each time you choose any lattice polygon and you run this procedure, you get a Gorenstein affine toric variety, and it's typically singular. There's only one case where it's smooth, where you take a triangle here, like a standard triangle. Most of these are singular. And then you can ask the question, does this singular affine toric variety, does it have a smoothing? And if it has a smoothing, does it have more than one smoothing? And so on. And there was work on that by Altman in the particular case where the singularity is isolated. But typically, for this one's not isolated. You see, whether it's isolated is necessary then what's equivalent to that all the edges of this polygon are length 1. And so you can make polygons where that happens, and the famous example in Altman's work is the hexagon, where you do this lattice polygon. And then indeed, every edge has length 1, you do the special ones, and in those cases you get isolated singularities, this is not isolated. And I want to talk about today how you can smooth this. And that there's two smoothings, which is known for the example, and how that fits into a more general story, which is a generalization of Altman's work also. Any questions so far?
The length one means like if you have like 1, 2 vector, is that length one?
Yeah, so for instance, the length of this diagonal edge is 1 in that sense. So it's not, so there's not a, it's the affine length. Yeah, you just count lattice points, how many lattice points you have. Yeah, I think it's a clarifying question. So here's a conjecture that was already reported about by Philip. It's by Corti, Philip, and Petracci. And the interesting thing is that they relate the smoothability and the number of smoothing components of such a singularity to something that's called a zero-mutable lattice Laurent polynomial. Yeah, zero-mutable Laurent polynomial. You've heard something about it. Let me repeat this for you. Let me say the conjecture. This conjecture says that the smoothing components on the versal deformation space of the singularity, there are several components. It's an infinite dimensional space. But since C2 is finite, you have finitely many equations giving this infinite dimensional space. And then you can have finitely many irreducible components. And these components of the smoothing, they are conjectured to be in bijection. There's a map here, one-to-one, conjecturally, to the zero-mutable Laurent polynomials. Polynomials. And how does this work? So let me do this in this particular example to illustrate how it works. To explain what is a zero-mutable Laurent polynomial. So this example, where we have this polygon of edge length 3 and 2, this has two different zero-mutable Laurent polynomials. So I draw it now 2 times. And the first one, they have names. The first one is called Tom, and the second one is called Jerry. Maybe you already did this. Mate, did you already do this example? Okay. So a convenient way to indicate the Laurent polynomial is to give to write numbers at the lattice points, which are the coefficients. So this Laurent polynomial will have integer coefficients, in fact positive integer coefficients. So I'm just, and all these. What's the difference between the two? So far they're not different. It comes with a further detail that I'm going to add. So the coefficients at the boundary are always binomial coefficients. There's no choice for that. But they can choose the coefficient in the middle. And of course, you want to choose in a way so that later on something works, and something that's supposed to work is that it has a zero mutation. I'll explain what it is. And in the Tom case, you have a 2 in the middle, and in the Jerry case, you have a 3 in the middle. So how do you translate a picture like this, where you have numbers at these lattice points, into a polynomial that may say what the polynomials are, and then you understand the general principle. So this polynomial that I call Tom has the shape 1 plus x to the 3. So secretly, I'm thinking of the horizontal direction to give me the x variable, and the vertical direction giving me the y variable. So when you expand this binomial, you get the bottom edge here. If the monomials are 1, x squared, and x to the 3. Yeah. And then I have to add more stuff to get the other things. So then I have to add, because I have a 2 here, I can write 2 times y. So y is the vertical direction that lifts me up to this level up here. And then I multiply with 1 plus x. This now takes care of these two coefficients. 2 times y gets up and then 1 in x direction, these two. And the only thing that's missing is a y squared, which is this one here. So I'm just adding a y squared. This is now it's in fact an ordinary polynomial, but more generally you can write down the Laurent polynomial. You could multiply this with any invertible monomial, any Laurent monomial, and then it would shift around the polytope. You only look at things up to shift. Right? If you multiply this with, say, x inverse, y inverse, or y something like that, I would still be able to do my work with this. So I'm just a generalist looking at all monomials. But for the purpose of this talk, you can pretend it's just a polynomial. And the other one is very similar. So here, a special feature was that because both of these are 2, I could write this binomial factor here because of 2. So there's a similar thing happening here because I have a 3 and a 3 here. I can write now more, if I slice it vertically, I get the binomial factor here 1 plus y. So the other one I'm thinking of, secretly I have been slicing this horizontally, and the other one I'm slicing vertically. So here's something like that going on. In the way I wrote it, I have done the slicing, and in the way I'm going to write the next one, there's the slicing going like that. So that means I have here 1 plus y to the square. This takes care of all the polynomials on the left at vertical edge. And the next one is just plus 3 times 1 plus y. Then I also have to multiply with x, because I'm shifting one over. And then I have just these 2, and they individually plus x 3 x to the square. The coefficient is 3, and the monomial is x squared, and then just have to add x to the 3. So these are these 2 polynomials that correspond to Tom and Jerry. Yeah? So you don't necessarily have to write it in this partially factored way. You can just expand and write all the monomials to the left, right? You can just write out it's 1 plus 2 times y plus y squared plus 2 times x times y. So you can just write it down without this factoring, but this factoring procedure will help me in the thing I want to do next. Hopefully you understand now, if I write some coefficients at these polytopes, how you can then write down the polynomial. So it's a very straightforward one. It's a nice way to code that. Okay, so these 2 normal polynomials, among other ones, you could put whatever other coefficients here. These 2 are special in the sense that they are both zero-mutable. I want to explain that next, what that is doing. So zero mutation, I hope that you have seen it a little bit already with Philip, Philip, because I'll do it a bit quicker. I'd like to do it a quicker way. So what are the zero mutations? So this procedure that you can apply. It's a bit of involves choices. It's not obvious exactly how you do it. There may be different ways to get the same result. Let's do this with Tom. I'm taking the polytope, I'm copying it again, and then I'm looking at an affine linear function. The affine linear function I'm looking at is already partially encoded in the previous way how I presented this. I'm taking a function which has level sets horizontal lines. So, for instance, the function will be constant on that horizontal line, it will be constant on this horizontal line, and on this one. And then I just need to say what is the constant value it say has at the bottom horizontal line and then one other one, and that defines the linear affine linear function uniquely. Yeah? And the function I'm using is I want it to have value 0 here on this line up there, this horizontal one, and then value 1 here, and then automatically we'll have value 2 here. So this is an integral affine function. So on this on the plane. And I use that to run a mutation. How this is going to work? So I'm looking at the monomial factor, binomial factor, which is generated up to multiplying with an invertible monomial by 2 lattice points that are consecutive on that horizontal direction. So that factor here is exactly 1 plus x. In this case, yeah? So you can place it somewhere over, and then you're multiplying this with some power of x to move it left to right. And I'm looking at this factor, and then my function values tell me how much I am supposed to removing that factor from the coefficients of the polynomial in that particular horizontal line. And let me demonstrate this in a moment here. So I'm claiming that there's an operation, which is called a mutation, where I go from this polynomial to another one that has as Newton polygon this polygon. So I'm going from this one to that. And what I'm doing is I'm subtracting the second power of 1 plus x from the bottom horizontal line. So the bottom horizontal line was this one. That was 1 plus x. So now dividing this, not subtracting, dividing this by 1 plus x squared. So what's then left is 1 plus x. And that's exactly what I get when I put these two coefficients here, because that means 1 plus x. And for the next horizontal level, so the last point here, I've rewritten this way, I'm subtracting 1 plus x to the power of 1. So dividing 1 plus x to the power of 1, so it really removes this factor, and I'm just left with 2y, exactly what you see here. And the top one does not get affected because it's a 0, so I would divide this by 1 plus x to the 0, so doesn't do anything, it just stays the one that I had before. And you already observe that the coefficients now again follow the scheme of having binomial coefficients at the boundary. And so the big question is, first of all, it's maybe a bit of a funny rule to do this thing that I could give an entire talk motivating why that would be a sensible thing to do. But then you can also see that it's quite rare that you first of all find that affine function, and then that these slices of the polynomial sense are then divisible by these powers that you're giving there. I mean, it's always fine if you do negative numbers, then you just expanding the polynomial. It becomes then has more coefficients. But if you want to divide it with the positive numbers, then it's very rare. You need to be careful that might not exist. Yeah.
How did you derive 1 plus x from the data?
What?
Do you know that 1 plus x is the polynomial that you are dividing by?
You're always dividing the binomial factor that you see on that horizontal direction, or whatever direction. If I have this affine, first I choose an affine function, affine linear function, with integral slope. So the level lines will always contain a bunch of lattice points, not all of them, but when you find one lattice point on a level line, you find other ones as well. And then take two consecutive lattice points on each level line. And they give you
a sum of two.
It's a binomial, yes, it's a sum of two monomials. And it's well defined up to multiplying with a monomial. So you can shift it along that.
There is always only one zero mutation that you can perform, or zero mutation at or by some polynomial?
No, there are other mutations you could do. Like as I say, it's kind of easy to do something with negative numbers where you expand things. I can make the polynomial bigger. But the idea is it's supposed to be zero-mutable. I want to make it small. The goal of this process, I will do another step right now after this. The goal is to make it small and actually get down to a constant polynomial. If that's possible, that's a definition now. It is possible by these kind of steps that I'm describing to take a Laurent polynomial and mutate it down to a constant Laurent polynomial, then we call it zero-mutable.
So I guess the question maybe is the same as he posed, but I didn't get the answer. So if you start with the polynomial 1 plus x cubed plus 2y, and I tell you to do the zero mutation, do you know what to do, or I need to tell you do the zero mutation in this direction or in?
Yeah, you have to decide what direction.
Okay.
Yeah, what direction? Yeah, just the affine function.
Okay. Affine function.
Mm-hmm. Affine function. Yeah.
What happens in higher dimension? Because in the level set it's not one-dimensional.
Then you do a similar thing. You take the full story if you want high dimensions also, then you have to specify a bit more than the affine function. You also have to specify what polynomial you want to mutate with. In high dimensions, you have then slices which are two-dimensional planes, and you can now mutate with other things. You don't have to mutate with a binomial. You could, but you can also mutate with a polynomial of higher degree. You can mutate with different things. So mutation generally is an operation like that where you have a polynomial which lives on that slice. Yeah, so the Laurent polynomial on that slice that you mutate with. I know some of you are representative theorists. You maybe know cluster geometry. By the way, I'm running in a Fjordite school next year. If you're interested in learning current state of the art of cluster geometry, welcome to come. Happening in beginning of June, second week of June. So mutation is a notion from cluster geometry. Zevinsky, Prokhorov, and then these cluster algebras, and there's a lot of interesting material. And they always mutate with factors like this one, 1 plus x. But you can generalize away, as I just said. You can also mutate with other polynomials. Within the cluster geometry, it's always mutation with such a thing. And it's very much related to that. So when the story is related, it's a generalization of these mutations from cluster geometry. So I'm not with zero yet. I've just reduced my polytope to a smaller one, and I can now do more steps like that. And in fact, now it's a bit easier to find more mutations. If you want to think along, you can try to find one. What I can do if I want to be efficient, I can make this level be 2, and this level be 0. Yeah, so when I have an affine function, which one I'm slicing vertically, and on this level set where the function is constant, it has value 0. On this level set where the function is constant, it has value 2. So it's somewhere level 1 is in between those two. And now I'm mutating the polynomial with respect to that function. And the factor that I'm dividing by now is 1 plus y. So here's like a 1 plus y. And nicely, it's divisible by 1 plus y squared even, and then I'm supposed to take squared because my level set here has value 2. So when I do this operation, I go down to this Laurent polynomial. I just have 1 plus x. So I'm not doing anything on this factor. There should be 1. There's 1 plus x that's left. But I have collapsed this vertical edge to just a point. So now with an interval, and with an interval, now you can collapse it to a point. For instance, by doing the affine function with these level sets, where I'm having 1 here and 0 here. So what the level below is 0. And now I'm collapsing this down to a point, the next step. Go from here, 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 here. And now we've mutated the Laurent polynomial down to a point. And whenever that's possible, we call it zero-mutable. And so I've just showed you that that is a zero-mutable one. I want to quickly also do the one for Jerry. This one's also zero-mutable by a different process of mutations. Here you already see the slicing that I might want to use for the first affine function to do the first mutation. What are the divisibilities? So if I look at this vertical part, this is divisible by 1 plus y squared. This one's divisible by 1 plus y, and this is not divisible. So the natural function you might want to use is 2, 1, 0, minus 1. Okay, that's a minus 1 showing up. I can divide this thing by that, and what I'm getting then, if I do the mutation, I get the following polynomial. Yeah, it's not only collapsing, it's also making it bigger at the end. Right? So there was a 1 here, but because of a minus 1, I'm expanding it. So the coefficients are 1, 3, 3, 1, 1. And that's what's happening when we have a minus. It's very easy to get things minus and it becomes bigger and bigger. It's easy to make stuff bigger, but it's hard to make it get it down to a point. But it's still somewhat better. You see the volume has decreased. That's not so bad.
And you need minus 1 there. Isn't 0?
Because I mean, the affine function is specified uniquely if I have 2 level sets, and then the rest is just given to me. So if I wanted to collapse this length 2 edge, so I wanted to value 2 here, and this was divisible by 1 plus y, so I had a 1 here, but then it sort of forced me that this is 0 and that's minus 1, because it's an affine linear function I'm describing, and then it has to get expanded. But that's not so bad. Now you can do a very simple step as you just here. You make this level have value 3, and that level value 0. And then the next step, mutation, you go down and collapse all that horizontal edge down to a point. You have this edge then, and then you do the next step where this again is 1, and some parallel here is 0, say. And with that mutation, you go down to a point. So you see that's also a 0 mutation. And now it's a little theorem, lemma, whatever you want to call it, but these are the only 2. On this polygon, these are the only 2 zero-mutable Laurent polynomials you can put there, so that the Newton polygon of the polynomial is this polygon, no more. And they nicely match with the 2 smoothing components. Also, that's where the names come from, Tom and Jerry. These names were given by Miles Reed and collaborators when they studied this singularity that you construct from that polygon. And they found these two smoothing components. It's also related to, these are determinantal varieties. You can describe the same singularity in two different ways as a determinantal variety of two different matrices. In one case, it's 3 by 3, and this is another one. And they found these two smoothing components that way and called them homogenic. And I'm having now a new approach to this. This new approach is with this zero-mutable polynomial from this work recently published like 2 years ago from Corti-Filip-Petracci. And today, I want to find yet a slightly different angle to this, some new perspective on it, where that might enable you to prove this conjecture. Yeah, I want to go in the direction of toroidal crossing spaces with this. And in order to do that, I need to do one extra exercise with this, which is so what I want to do is, I want to, whenever I have a polygon with a zero-mutable polynomial, I want to associate to that a toroidal crossing variety, that's a translation of a normal crossing variety, toroidal crossing variety, together with a singular log structure. Yeah, toroidal crossing variety with a singular log structure. And in order to do that, I need to associate to this stuff partitions. Yeah, I can write down two partitions, which is sort of in this game already. Let me explain how it works. I'm looking at the divisibilities, which were meaningful in the mutation steps that I did, by these binomial factors, and you find that I basically forget the particular mutation, but I'm looking at these slices that are parallel to the edges. Right? Every edge has integral slices that are parallel to it, and I'm looking at on that slice is what the polynomial divisibilities by the binomial factors. If you look at the slice here, then the polynomial is divisible by 1 plus x to the third power. We already used that. If you look at the next one, then it's by first power and 1 plus x, and here it's divisible by not at all. Yeah? But now I do that also for the other edges. So if I go and slice it through by these slices, parallel to the edges, you also go parallel to the edges. And what are divisible by 1 plus y for those? This one has divisible by 2. This is by 2. Here it's just divisible 0, because that is not divisible because they're two different coefficients. And so I get 2, 0, 0. Check these divisibilities for all the parallel slices to the edges. And I do the same here. So here the horizontal slices, or the slices parallel to the bottom edge, I get divisibilities 3, 0, 0. 3, 0, 0. And for the other ones, I get exactly that here. So I get, for the minus 1, I get 2, 1, 0, 0 as divisibility. And then I'm writing down a partition for that. So these divisibility give me the partition of the number 3 as 2 plus 1. And this gives me the partition of 3 as just 3. And here I get the partition of 2 as 2. And here I get the partition of, I take the differences, I get the partition of 3 as 2 plus 1. Make sense? So this should be, that's what the maximum here is 2. So this is a partition of 2. And this here, here I have the steps. You look at the steps are 2 and 1. So yeah, that's a partition of 3. We get a partition of 2. And here I get a partition of 3 as yeah, so this is a you take a look at the differences. So 2 is 1 plus 1, and here this is 3 is 3. So the vertical sides always give a partition of 2, and the vertical ones give a partition of 3. And then you write down the Young diagram for that. And then you dualize the partition. Okay, when you have a partition of some number, write the Young diagram, something like this. That will be writing the number 5 as 3 plus 2, when you look at it vertically, but then you can dualize it. When you slice it the other way, you write the number 5 as 2 plus 2 plus 1. That's a dualization of a Young diagram. I've never seen it. So I can dualize these partitions. Yeah.
This 5 equals 3 plus 2, it cannot be use the F functions. If you have 3, then it has to start to 5, 3, 1, or.
I look at the divisibilities, and the maximum divisibility you can have for 1 plus y is 2, because the length is no longer that here. And then I check the divisibility steps as I go down. So this has 2, the next one, and then that gets you this partition.
Yeah, but it will always. Okay, yeah, sure. Yeah. Sorry.
And then dualize the partition. So let me use a different color to write the dual partition. It'll be black. When you dualize the partition 2, you get the partition 1 plus 1. This will come useful later. When you dualize this partition, it's self-dual. 1 plus 2 stays 1 plus 2. If you take the partition 3, that becomes a partition 1 plus 1 plus 1 as a dual. And the partition 1 plus 1 becomes a partition 2 as a dual. All right, we'll use that in a moment. So let me give you a quick introduction. What is a toroidal crossing scheme? Toroidal crossing scheme with single log structure. Yeah.
So if we go to one dimension smaller, so just I take a segment.
Yeah.
Then we do then you will have a quotient singularity. And we have the different smoothing. This combinatorics, which means that combinatorics of the smoothing components there. In that case, you have only one step here. Yeah, but it's all of them just one step you in the segment.
Yeah.
No, not A. We do the quotients. So this is only for A.
This is there.
Yeah.
So the other quotients you can have any.
This is Gorenstein.
Yeah, the Gorenstein.
This is
Yes,
Gorenstein.
yes.
That's
Sorry. Yeah.
That's
No, it's a very good question. It's a very good question.
yeah, because it was.
Yeah. I thought about this at some point. There's also a game you can do with all the ones, but it's a different game.
Okay. So the Gorenstein is
That's where that's a good point. So let me give you the general procedure how you associate a toroidal crossing space to this. Remember, we took a cone over a polygon, and then we took the dual cone. And the dual cone has a particular feature which reflects the fact that our original cone was a cone over a polygon. Or you can also say that it reflects the fact that the associated singularity is Gorenstein. It has a particular interior ray, the Gorenstein ray. Yeah, so it has an interior ray, the Gorenstein ray. Some people call it the Gorenstein element that generates this ray. Because the singularity is Gorenstein. And then what we do is we do the simple subdivision of this dual cone along the ray. We can all call it star subdivision. Yeah? So in our example, the example is a bit special in the sense that the dual cone is isomorphic as a lattice cone to the original one. That makes it a bit more convenient for me, though, because I don't have to introduce a new cone. The dual cone isn't actually a new one, it's isomorphic to the original one. So the dual cone is really also just the cone over a polygon. That's unusual. Normally the dual cone will not be a cone over a polygon, but this one is. And the Gorenstein ray is generated by this interior lattice point. Yeah? So the polygon has it's special in the sense that it has an interior lattice point, unique one. And that's the generator called the Gorenstein ray. In the general case, there's not a unique lattice point. It's not a cone of a polygon in the general case, but there's always this ray in the middle, the Gorenstein ray. And by central subdivision, I mean that I'm doing the coherent subdivision of this cone where I do star subdivision along this. So I'm breaking up this cone in 3 cones. Now it becomes a fan. It was a fan, a cone before, now it's a fan with those 3 maximal cones coming from the star subdivision, that fan I call sigma. And now I'm not taking the toric variety of this fan, which you can also do, but I'm using the fan to write down a Stanley Reisner ring, different thing. So that goes as follows. There's a ring here I call C of sigma, and as a vector space, it's really just the ring I had before for my singularity. So the second was the C3 dual. But it has a different multiplication from the monoid ring. Not the monoid ring, it has a different multiplication. The multiplication goes like this. If I have 2 monomials, and I write these monomials z to the m times z to the m prime, where m and m prime are elements of this monoid, then this multiplication is defined to be what you would get also from the monoid ring, only in the case where m and m prime are elements of a cone. That's called tau for some cone tau in the fan. Yeah. So you only get the ordinary multiplication. Oh, well, sorry, I should write here plus m prime. Yeah, that makes it clear. And or it's 0 otherwise. So you see, it's a default multiplication. Sometimes just the original one. In the original setting of my toric singularity, it was always this one. That was the definition of multiplication, because I use the monoid multiplication to define multiplication of the ring. But here I tweak it and make it 0 if there's no cone that contains both of them simultaneously. This is called a Stanley Reisner ring. This concept, Stanley Reisner ring, it's a particular case of that. And so if you look at the affine variety, the affine scheme, the spectrum of this is now reducible. Previously, was a normal scheme, was reducible, but this Stanley Reisner scheme is reducible, and it has 3 irreducible components. And the 3 irreducible components correspond to the 3 maximal cones in the subdivision. Yeah, there's 3 red maximal triangles. There's a cone of each of those triangles, and the affine toric variety coming from the cone over one of those triangles is one of the components. And we have 3 such components. And they're all non-isomorphic. In my picture looks similar, but they're different components. So this is the union of one component is an ordinary smooth A3. The next component is a CA1 singularity. And the third component is a CA2 singularity. So this reflects the fact that you had these edge lengths of different lengths. There was an edge length 1 that gives you the A3. Edge length 3 here gives you the CA2. And edge length 2 gives you the CA1. Which means it's an A1 singularity times an A1. It's a curve worth of compound A1 singularity. So I have these 3 components, and then these components meet each other in the combinatorics that you see in the picture as this fan. So any pair of them meets in an A2. Any pair meets in A2, which is spanned by the edge between the 2. Yeah, so the edge is between the 2. So they meet in A2s, and all 3 of them meet in an A1. And that's the center ray, the Gorenstein ray. You get this geometry from the center subdivision. And it's toroidal crossing in the sense that if you are writing down monomials along, so if I look at the intersection of all 3 of them, the intersection of all 3 of them is an A1. And along that A1, I can write down an equation for that scheme. And it's going to be this one. U times v squared times w to the 3 is 0. So you see this is like a generalization of a normal crossing. Normal crossing would be u v w 0, but I have these powers here. It's very close to normal crossing. Yeah, it has these powers. It's toroidal crossing, and how you get that is you take the monomials u v w to be the outgoing directions from that A1 that has all common, and you have to use the ones where this one is V, and this one is W, and this one is U. And then you'll see when you take the corresponding monomials that are the difference of this point with that point, that's u, and the other one is v, and so on. They have this relation. In the lattice, you get this relation. Yeah, so that's how you can get a toroidal crossing scheme from a lattice polygon. Yeah, and all the way. Lattice polygon gives you a toroidal crossing scheme from the standard right array. And on this toroidal crossing scheme, I want to put a log structure. Yeah.
Spec of this is just about.
No, the spec of this is it's a ring, and you get.
Yeah, but I mean that's what is called toric boundary. Like the spec of the.
No, if you look at this as a toric variety, it's a threefold, and the boundary will be twofold. But my thing is a threefold. It's a different construction. Yeah.
It's boundary times A1.
Okay.
Every
Yeah,
element
that's
in
true.
the cone can be uniquely written as an element of the boundary because multiple of the Gorenstein decree, and then you see the
Okay.
case.
And now I want to tell you how to get this single log structure on that Stanley-Reisner scheme.
This is not, there are more equations, aren't there?
Yeah, there are more equations. It's typically not a complete
So the
intersection.
hypersolve the singularity.
So how to get this single log structure? So I'm actually interested in smoothing it. I want to smooth the Stanley-Reisner scheme. The Stanley-Reisner scheme is very singular. It has three components. It's a generalization of a normal crossing variety. I want to smooth that scheme. Make it, put it in a family with zero fiber smooth. And I claim there are two ways to do that coming from Tom and Jerry. And the smoothing is governed by a log structure. Yeah, just like we followed Zeeman star, we just log deformation theory. And so I need to put different log structures on there to get different smoothings. And the log structure will be the following.
That will give us smoothing was of the original one.
Yes, but that's not so easy to show. Yeah, that is true. So what I'm drawing here is the singular locus of this reducible scheme. Now, the scheme has three components, and the singular locus contains of all the double, where any two components meet, you get singularities. And so I have three components of the singular locus. These are three surfaces inside that. And on these singular, on the single locus, you are supporting a section of a sheaf, which gives you a log structure. Okay, so it's a theorem that log structures on this thing come from a sheaf, sections of a sheaf, and then the singularities are where the section of a sheaf vanishes. And I'm drawing now the vanishing locus of the section of a sheaf. Yes.
You didn't see it, but it's the one that I introduced in the lecture.
Oh, you did that. Fantastic. Yeah. LS it's called, right?
Yes.
Yeah, fantastic. So this sheaf LS, great that Simon talk about it. And then you can choose various sections of LS, and they give you different log structures with singularities. But I'm giving you very specific sections that vanish in a very particular way. And for Tom, I want them to vanish in two lines. Yeah, so these are two lines that meet in a point, and the point is on top of that is on the triple locus, where all components meet. And then they meet over here, they meet in a parabola, so a conic, that is tangent to the triple locus, and also in the point where the other two lines come in. But there's also another line that's transverse coming in here. So you see, this is a degree 2 curve, this is a degree 3 curve, and there's a degree 1 curve in the back that also meets in that point. So there's this one point, everything goes in that point. Very bad singularity here. And then away from that, I have these configurations of a cubic curve, a conic curve, and a line in these three double locus components. And why that is, it's informed by the dual partitions. Let's go back to that. So when I did Tom, I wrote down these divisibility steps and the partitions, and then dualized the partition. The dual partitions are written down here. One was 1 plus 1. That translates as degree 1 plus degree 1, because these are two lines. These are the two lines that you see here, a line and a line. And the other one is 2 plus 1. That means a conic and a line. That's the thing you see here. Yeah. So the partitions inform me of what geometry of section I want to put here. On the Jerry one from that partition, I want to have a 2, so that is a conic, a parabola. On this component here now receives a parabola that's tangent to the triple locus, and the partition 1 plus 1 plus 1 means 3 lines. So over here you get 3 lines. And the back there's always just a line because there's no choice for that. So these are 2 different sections of the same sheaf LS, the sheaf that classifies log structures on that toroidal crossing space. Different sections with very specific geometries of where they vanish. Yeah? So each double locus is an A2, and in that A2 you have a curve, but very special curve, and they're very far from generic. So in the previous work that Professor Simon had reported about, where we prove a theorem about smoothing of toroidal crossing spaces, we always assume with the log structure that we choose is generic. This is the opposite of generic. This is extremely special. But interestingly, these extremely special ones are the only ones you can resolve and smooth. If you chose a generic one, you would not be able to smooth those ones. So it's a very different paradigm shift. How much time is left? 15 minutes left. Yeah, fantastic. So next I want to explain, so the next step in being able to smooth those singularities is to actually resolve. Yeah? You've seen this a couple of times in singularities theory that smoothing has something to do with the resolution or quotient singularities. That these partial resolutions have to do with the smoothings, which are barren work. So instead of smoothing it on the nose, which is in fact hard, I start to resolve the log singularity. And then once it has fully resolved and I'm log smooth, the smoothing is quite natural because I can then apply log smooth deformation theory. And I'll get a smoothing from the work that Zemo reported. Yeah? So the smoothing really has to do with being able to resolve it. And not just resolve it, I want to stay in the Calabi-Yau. Remember, we're actually using a monotone Todorov version of the theorem. So I need to stay in the Calabi-Yau realm. This is Calabi-Yau. But I don't want to blow up too much. I want to have a log Krappen resolution. So I need to be very careful. Have a log Krappen resolution of these. And the fascinating thing, they exist. Generally, if you write down some whatever single locus, will not exist. But these ones do have. And I'll explain to you how I construct them. And in the process of constructing them, I'll construct them in some inductive process, which has something to do with the mutations. So we'll come back to that. And then I'll conjecture that it works in very general. Yes?
Would you explain how from a Laurent polynomial you get a log structure or?
Yeah, I basically did. So
Yeah, but
yeah, so do you want to repeat it or?
yeah, I mean, yeah. I mean, I get that this is the zero. I mean, but yeah, okay, please.
Yeah. So if you have a zero-mutable polynomial like here.
I get how you got those curves.
Okay.
Still, what is the log structure?
The log structure is the one that singularity curves. Okay, I can say a few more words. So at this intersection of the 3 components, it's an A1, and I have this equation for the scheme. U times V squared times W to the 3 is 0. And if you want to make a deformation of the space, you will have to put something on the right-hand side that's non-zero. And what you put there is a deformation parameter T, but it may plus a section of LS. So if you choose a log structure, the log structure will place some factor here to the, if you smooth it, that's a smoothing, right? To the right end is T here. But there's an extra factor here that produces singularities of the total space of the smoothing. And that's just some polynomial F. In fact, this F is a section of S, what Zeno spoke about, the log structure. And that F vanishes precisely in those curves. Okay? It's a section of this LS sheet which vanishes precisely in those curves. Yeah. In the normal crossing space, it's a section of the T1 sheet. Okay? You can relate the LS sheet to the T1 sheet. That doesn't, maybe works here as well. I'm not sure. It might be a section of T1 sheet. You can interpret that way. So it's an X thing. But this thing vanishes there. And the total space of deformation will have singularities then there. But I know what to choose if I have done my combinatorics. So how to resolve this guy? Let's go back in a simpler case to study how resolutions work. Here's a more simple example. I'm looking at the family xy equals tw. It's reminiscent of that. So if I reduce the left-hand side to just two variables, and the right-hand side is t times f, and my f is my w. Yeah. So you know this example, of course, every singularity theorist has seen this before. This is a degeneration of surfaces. T is my parameter, my family parameter. And in the simplifier, when t is 0, I just have two affine planes that meet in an affine line, like this. But the total space of the family has an A1 singularity. So that's also the equation of an A1 singularity in 3 dimensions. So that's my central fiber, that the total space has an A1 singularity. So somewhere there's a point, it sits in fact on the double, the section of the two components, where the total space has a singularity, A1 singularity. And that A1 singularity is also the singularity of the log structure. Yeah? So in this example, if you take the Debsol log structure coming from T, and the central fiber, we see the log structure that's singular exactly at the point where the total space has a singularity. And if you just look at the central fiber, you don't know about the total space, but the log structure still knows about there was a singularity in total space at that point. So it's exactly an example where we have this f. It's one dimension lower, so instead of curves, I really just have that one point. It's just one point. And I can resolve that log structure, as Javier pointed out, by knowing there is a total space. I can use that as an example, because here I don't have a total space yet. I want to construct it. I want to smooth it out. I don't have it yet. But here I have one. It's written down here. I can blow up the toric divisor, the toric variety. I blow up the toric Weyl divisors. You choose one Weyl divisor, you blow it up, and you get a small resolution. There are two choices. Either you put a P1 into this component, that's small resolution, or into the other one. Now these are two small resolutions. There's also a big resolution where you both simultaneously, but then have a new divisor. You don't want that. That's not Crapet. Now these two are Crapet, small resolutions. They're related by a flop in the total space. So these are the resolution of an A1 singularity in 3 dimensions. Yeah, it's a conical. So there's a flop between the two resolutions of a conical. Right. But this example tells you what you should expect if you go one dimension up. I want to now resolve these two, which is a much more difficult process. But I already see here that there's choices. There's not a unique one. And the choices have to do with which of the two components you want to leave untouched, in a sense. And the other one gets exception otherwise. So let me hope I can finish the entire process of blowing up Tom. Okay, let me try to blow up Tom. So generically, at a single point, when you go anywhere here, like at a smooth point of these curves, then locally there, it looks exactly like this two-dimensional example, product with an extra trivial direction. Yeah? And then you would have exactly these two choices, locally at all these points. But then, of course, it's very difficult to do something at the triple point where everything comes together. It's very hard. What are we doing? In the first step, so in order to guide my process of resolution, I want to remember that there was a zero mutation going on. I had this big polytope with the edge length 2 and 3, and then in the Tom resolution, I first brought it to the smaller one, the edge length, and then I went to the edge and then to the point. And this zero mutation informs me of certain choices that I can make in this resolution process. This was a discovery that Alessio and I had just 2 months ago. So here, remember that in this process here, I was basically deleting this 2 by 2, and then I was adding a bit here. No, sorry, that was the other one. I was just deleting in this case. The example. You can say you're deleting this part here. Yeah? So I'm removing this one in the first step. It's getting removed. This is a conic. Yeah? So if this is a Newton polygon, it has edge length 2, 2, 2. Newton polygon of a conic. Where do you see the conic? Well, here, there's a conic. Yeah? So it somehow tells me that I have to do something, I have to remove this conic. Well, you can't technically remove it. It's the log single locus. But there's something funny you can do. You can change the toroidal cosine space structure by looking at the opposite component from the conic. One of the three components of this space is over here. That is a singular component. The singularity of that component along this triple locus has something to do with the appearance of the conic here. If you change this component, replace it by a different one, so you change the toroidal crossing space, you can make this conic disappear. Yeah. So you replace this component with something that's slightly less singular, and instead of having three pieces here aligned into conic, you can make the conic disappear and the line stay. And that's corresponding exactly to the singularities you get from this polygon. Yeah? So you change the toroidal crossing space by replacing this component. This is trick. Replace this component. That's not allowed if you want to do resolution. You're not allowed to replace a component. That's much more serious than doing a bidirectional transformation. It's not a bidirectional transformation. But I'll put it back later. I remove it first, replace it with something simpler, and I get the original back later. That's the idea of the resolution. So we replace it to get a simpler situation where we then have the story that's governed really by this triangle, which is called the A1 triangle, because the singularity that it belongs to is an A1 singularity. And here I only have two lines here, and a single line here and a single line in the back. I haven't replaced that component. I haven't done any resolution. I've just made my story a little simpler.
Is that Gorenstein, the new one?
It's also Gorenstein, yeah. Yeah, it stays in Gorenstein.
So if you go to you see the point in the blue.
Yes. Yeah. And then I go further. So the next step in the mutation here is getting me down to an interval. That you can also achieve by replacing a component, and you're going to replace this component opposite to the two lines. So in this step of going to the interval, you're killing the two lines, and then replacing the component over here. This has a singularity, replacing with this smooth component, and then you get yet another toroidal crossing space. Where the log single locus consists of only two lines. Okay. And now it's easy to resolve. Because now I'm in a situation where it's basically, except from that there's an extra thing coming out here, it's like a two-dimensional situation times in trivial direction. So I can blow this up. There's two choices to blow it up, in either direction to the left or to the right. And I'm choosing the direction which does not touch the component I've just been replacing. So I blow this up, and over that single locus I get a P1 bundle in both components. This is the small Kraken resolution. It's now P1 bundle over the single locus. And then once I've done that, I can put back the component I replaced here. Yeah? Return the component that was originally there. And then what happens when you do that replacement? You still have that P1 bundle. So that lives in two components. It was already the case before. But now because I'm replacing the component here, I put back into the gain the two lines that I had removed when I replaced that component. They come back now, but they come back in a more convenient place. I reintroduce these two lines, but now they become the strict transform of that blow-up. So they now end up being here. They're still in this double locus component, but they come in and first of all they're disjoint now because I've blown up this point. They're disjoint, and they come in here in this double locus component. So really, we can draw them over here. So they lie in this single double locus component, and they meet this exceptional P1 here in 2 points, 2 different points. And that is again easy to blow up. Yeah, so I have this log single locus here. It doesn't even meet the triple locus. It's very very easy. I can blow it up in either two choices of the neighboring components. It's again a situation of a two-dimensional case times the trivial direction. Because it sits in two components only, I can choose which I want to put the P1 into. Let's choose just, which one will I choose? I know that I still have to do a step afterwards, where I did replace, in the beginning I replaced this component. I want to put it back eventually. So I'm doing my blow up away from that component. I don't want to touch it. So I'm blowing up to the front. So the next step, I blow up these two purple lines. And they get P1 bundles over them. And they live in this front component. Yeah. Now I would like to put back the original component I had in the top left corner. I want to put back this component that I had replaced here. But I cannot do that now because there's a bit of exceptional. The red guy here has walked into that component. To get it out of there, I flop it out. I use Mori theory in 3 dimensions to flop that entire P1 bundle, the red thing, into another component where I don't have to do the replacement. So I'm flopping it all the way over to that component over here, which I had replaced at an earlier stage. Yeah? So I'm flopping that P1 bundle. And then the situation looks like this. So we'll be in this component to the right. Just flopping it over there. And the two purple guys, they're still around. They live here. Then they go into. See, I don't exactly know where exactly they go, but they stay in the component where they were. And this flopping process has freed up this component. It's now like the one it was after the replacement I made, so I can unreplace it and put back the original. Yeah. Now put back the original component in here. And as you do that, you reintroduce the part of the log-single locus that you had removed with this replacement, and that was the parabola. Yeah? So in that process where I went from here to here, in the replacement, I killed the parabola. That now comes back as a re-replaceable component. But it comes back in a more convenient place. So it's now looking like this. There's these two guys. There's the flopped P1 bundle over here. And I get back a parabola, and it's now in a very convenient place. Namely, it will just come, see where it was. So it was in this double locus component, so it's going to be here again. But it's going to be disjoint from the triple locus, just a parabola of log singularities here. And the final step again, I'm back to the two-dimensional situation. I can just choose which direction I want to blow it up in. Yeah, it doesn't matter anymore where you do it. Let's maybe blow it up into the front. You get the P1 bundle over the parabola, and voila. This thing is smooth. This is log smooth. It's a log smooth and furthermore crappened resolution of the original log singularity. And now you can run the smoothing machine and smooth it, and it's the smoothing. It reproduces the smoothing of Tom of the toric singularity. And the conjecture is that Corti Gräfnitz is also working on this, Tim Gräfnitz, and I have that this generalizes and works for all lattice polygons. Yeah. You always get the smoothings of this Q-Gorenstein variety from that. Yes.
You said you want to apply my theorem, but this thing is not proper.
Yeah, you have to compactify it. Well, in fact, the way we use it, what we want to do with this is we want to, as I said in my title, I will construct Fano manifolds. This is all the at-mine situation so far. But there's an extra key feature in this. So maybe
I
kind of
can prove that this. Okay, so this thing gives one of the two resolutions x, y equals w out z.
let me tell you something key feature. So when you do these resolutions, the blow up, I was very naively just I blow up this and blow up that. But they're very crucial types of blow up that also allow me to do these flops. They are divisorial extractions. Yeah, divisorial extractions is a terminology from Mori theory. Divisorial extraction. It's the opposite of a contraction. And divisorial extraction have a property that they either do not exist. So if you're in a threefold, you have a curve. You want to do the divisorial extraction of that curve. It may not be there. Sometimes it doesn't exist. Because it has various properties supposed to satisfy, like being the opposite of extremal contraction. Sometimes it doesn't exist. But if it exists, it's unique. And that's the cool thing. So we prove these divisorial extractions always exist, and then they're automatically unique. So these blow-ups that we construct have a certain strong uniqueness to it that allows us to glue them together in a more global setting. So when you have a more global geometry, like a Toroidal crossing space with many singularities, you can resolve them and very controlled and glue the things. You can glue these resolutions to have a global resolution of a singular toric, block toric Fano. So we construct log resolutions of single log Fanos and then run the smoothing, and then we're in a compact setting, so we can run the theory. Yeah, so I have to compactify if I study the original problem of this conjecture, then I have to compactify. But in my application I care about with the Fanos, they're compact. And I use this story. Yes.
So if pi is a blow up, is R1 pi lower star theta 1 0 or not?
You're asking whether these are.
If the deformations that are coming from the revolution are locally rigid.
I don't know. That's the next project.
And can you give this process an explicit equation so that we can compute this R1 by lower star theta 1?
No, explicit equations are very tricky because it's typically it's not computer section. So you don't want to work with explicit. Yeah.
Understand correctly, you basically just do, I mean, if you take the reflexive three-dimensional polytope,
Yeah.
and so you describe what you did on one class.
Yeah.
That's
So Mate, this is exactly, so when you talk about a toric Fano threefold, that's given by a reflexive three-dimensional polytope, that also has a central subdivision, just like my cone thing had. And then you get a toroidal crossing space again by Stanley Ricer thing, so you can do a very similar story in the compact setting. And then exactly, yes, these singularities show up, different singularities show up in different places.
But you cannot just do the affine case because it's not proper. You need to have I mean, this is the story that you described.
Yeah.
What you're doing on each, but you have to take all of them together.
I can locally produce these resolutions locally.
Yeah.
And I can glue them because of the uniqueness properties. Okay, so there's a discrete set of choices of, on which side you blow up these devices, with all the extractions, to which component you do. It's a very finite set of unique choices, and you can always glue it globally. You can make the choices such that they glue globally.
But still, like, there's any, you need some properties, right, to then do.
Yeah, but the toric variety is proper now. If I'm doing to Fano, proper compact Fano toric variety.
Yeah, but this, but then you cannot do just like efforts. Just like.
Yeah, I can. If you want, prove your conjecture.
Yeah.
I need to compactify. Yes.
So then, and there is no restriction on the facet. You just take one zero-mutable on one facet. Yeah, I mean, any other, no restrictions.
No. Okay.
That's fine. Because at some point, Alessio and I think Andrea had some that there might be some obstruction.
Oh, you mean whether any toric Fano is smooth? Of course, there are many ones that are not smooth.
No. Like when you pick those zero-mutables, that I mean, I think at some point there was an idea that you have to. I mean, it's not like you take arbitrary two zero-mutables, right? So there needs to be some. So, for example, this admissible condition.
Yeah.
Alessio's work, there is some.
Yeah. You can't try to get rid of those conditions.
So again, back to the question. So the two smoothing, the two minor factors will be the same. So if you smooth both just the components.
Which example are you talking about now?
So if you smooth then this.
Yeah, the totality. Yeah.
In the sense that you make it normal crossing and smoothing.
Yeah.
And that smoothing, the generic fiber will be the same as the generic fiber of the
original.
Of the original.
Undegenerate, yes. And that's something one has to prove. It's not trivial.
Do you have any control using the combinatorics of these to the numbers of that anything?
We hope, yeah. We hope. Should be possible. That's no work yet.
This is an optimistic statement, or you really think it's? Because this sounds really hard.
Well, I mean, what's solid is, Corti had this grant in Imperial College where he ran through all these three-dimensional reflexive polytopes. I don't know how many there are, like several thousand. And he constructed some enumerative data like Hilbert functions from them, some other things, and he could identify which ones should have smoothings which give you the 105 smooth Fano treatments that we know. And he had evidence that you can get them all from these reflexive guys. So it should work, but to pin down, okay, to prove actually, okay, this is these invariants, and I can compute it from that.
Any other questions?